So it's a pleasure, to um, to share this moment with you on the opening of our 16th International Conference on Finite Fields and their applications. We have an exciting, program ahead, and I'll have to make a few announcements. The first one, we are honored to have here Professor Kalinka. She's the director of the Institute of Mathematics, Mathematical and Computer Science Institute here at the University of São Paulo. Professor Kalinka has kindly agreed to come here and share a few comments, welcoming comments. So please join me in, receiving Professor Kalinka here, please.
Good morning. It's a pleasure to have all of you here with us. I know that this event is very important, and for ICMC, it's a huge pleasure to have you here. I'm the deputy of the deputy director of this institute, and in the name of Professor André, that is the director, I want to give you the very warm welcome. I know that it's a little bit cold, but a warm welcome, and I hope that you have special moments and that you can share a lot of insights and new ideas here at ICMC. I know that you are not in a place that have beach, but we have a very nice campus, and we have also a secret garden. Maybe you can see some toucan there. And it's really, really a pleasure to have you here. Thank you, Erivelto, to bring this event for ICMC and Brazil, and hope you enjoy a lot this opportunity to share ideas and knowledge. Thank you very much.
Thank you, Professor Kalinka. Your support means a lot to us. So I need to thank many people for this conference. So now, a special thanks for those who made this possible, especially because the FQ conference is the first time the FQ conference is taking place in Brazil, the first time ever. So first, my sincere thanks to the FQ conference steering committee for trusting us, giving this opportunity for this historic honor. I also want to thank the organizing committee, Professors Claude Corlet, Cícero Carvalho, Sirhen Mesnager, Gary Mullen, Daniel Panario, César Polsino, Cecília Salgado, and Luciane Coase. Many of them are here, our colleagues. I also want to thank the University of São Paulo, especially the Office of Events, our colleagues Fernando Marília, Reginaldo, and Ayrton for the tireless work. I also want to thank our transportation team for safely bringing many of you from the airports to São Carlos. It was great. And of course, I want to thank the funding agencies, FAPESP, CNPq, CAPES, and Elsevier, for all the support. And now a special thank for our team of graduate students. Please stand up. Please let's applaud this. So this team will assist with practical things like going to the other sessions. And I mean, if you have any kind of question, whatever you want to ask, of course you can ask me during the breaks, but you can also ask to any of them. So thank you very much, you guys. Okay. And of course, I also want to thank many other people and other names who really worked behind the scenes, especially, let's say, André Duarte, Alex Freitas, and many other colleagues. And now let me just mention, let me just bring some information about important locations. So you all know you have parallel sessions. One of them will be here in this room. which is called Auditorium Professor Fernão Germano. This is the room 6001. The other room, right next building, next door, it's on building 5. It's supposed to be room 5003, but we just had a technical problem, and it's going to be switched to 5001. But don't worry, I mean, our team will guide you guys there. That's not a big deal. Also, let me just remind you, we have coffee break and poster sessions. There will be a building right behind you guys at the hall, in the hall of that building. That space is known as Professor Leubel's hyperspace. So you'll be there, later. It's quite easy to reach that place. And also, I mean, just in general, if you have questions, feel free to ask me, during the breaks, or ask any, any member of our teams here. And also for lunch, there will be, I mean, there are lots of places, lots of restaurants around the campus. I mean, most of them like a walking distance, perhaps 15 minutes at most. But you also have a cafeteria here, on the campus. So, I mean, if you want to find a place to go have lunch, for instance, you can ask me. You can ask any of them. I mean, it's fairly easy. And probably, I mean, after the last talk in this morning, I mean, there will be groups of people going to different places. Of course, you cannot bring all the 100 participants to a single place. This is going to be a mess. But we can split and go to different places. I mean, it's fairly easy. You'll see. Let me just remind you. Today, at the end of the day, after the last talk in the afternoon, there will be a welcome reception at 6 p.m. Again, it's a very, it's a place nearby. It's walking distance. But I'm going to ask you, after the last talk in the afternoon, please stick around. We'll probably, wait for you guys here at the building, at the hyperspace, Professor Leubel's hyperspace, and we all walk together to the location. Okay, so don't worry. I mean, it's fairly close, but I mean, it's better if you just go all together there. And also, okay, so I mean, for now, let's just focus on the the heart of our conference, which is, I mean, I'm eager to see many nice research results that you guys are here to share, and that's pretty much what you're gonna do next. So for now, I just want to welcome you all, and I'll thank you for being here. Okay, that's all for now. And in a couple of minutes, Professor, no, if Professor Luciana Close, yes, she'll be the chair of our first. Yeah, no, sorry, she'll be the chair of our first plenary talk. Yes, and Maria Montanucci will be, of course, our speaker, our first speaker. But you will still have a couple of minutes, so we can wait for now. Oh, by the way, I mean, since I still have a couple of minutes, there will be a few other announcements that I'll be, bringing, during the day, perhaps tomorrow and after. For instance, right at the entrance of this building, you see this huge screen. There you see the conference program. There is also Wi-Fi specific for the conference. There you see, just type, you see the username, password. And also, if I know some of you, still have to, some of you have to do the registration. You can go there during the break. That's not a problem. And also, let me remind you, you have 3 social events. We have the welcome reception today. We'll have the lunch, a special lunch on Wednesday, and then the conference dinner on Thursday. So it's all covered by the registration fee. But I mean, if you need more, and the location and the time, we're gonna. I mean, there will be arrangements for those events, but I'll bring more details later. Okay. So for now, let's just wait a couple of minutes until Luciano. Okay, so there is another request. All the chairs, please, you're gonna have to use this microphone, okay? You guys who are being chairs for this next sessions. And just to remind you, I mean, the next building right here, that's where the other room is located. Don't worry, people will bring you there, right after I mean, we will have the plenary talk here, then the coffee break, and then the parallel sessions we will start. Okay, so it's quite easy, 1 minute crossing this garden here. Okay, so yeah, that's all for now. This one. Thank you. Okay, so feel free to.
It's on. Okay.
The light on, the microphone is on.
Perfect.
Which one? Control L. Just type the Windows Control L plus L.
All right. Thank you.
Right, forward, backward, and this right one.
This is the point. Okay. Thank you so much. That's fine. Yeah.
So welcome everybody here to, Ferro, to this conference. It's very nice to have you all here. And I'd like to introduce then the first speaker of the day. It's going to be Maria Montanucci. She's working at the Technical University of Denmark. And she's an expert on algebraic curves. And so she's going to talk to us about algebraic curves in positive characteristics in their birational invariants. So welcome, Maria.
Thank you very much, Luciane. And of course, let me start by saying a huge thank you to the organizers for allowing me to be here. Useless to say, it's a huge honor. So thank you very much. And thank you all for being here today. So as Luciane said, I'm going to talk about some algebraic curves in positive characteristics. And well, this is more or less the outline of the presentation that I have for you today. I would like to start by fixing some, standard notation and terminology about algebraic curves with a particular focus on the so-called birational invariance of a curve. Then I will zoom in a particular class very well studied of algebraic curves over finite fields, the so-called maximal curves, and I will try to explain in few words why people cared about those objects in the literature. With this background in mind, I will analyze with you today 3 problems that I studied in my career. The first one is how do you construct and classify maximal curves, particularly using birational invariants. The second one is, do maximal curves have a very special geometry? What can you say about that? And lastly, I will focus on the birational invariant called automorphism group and try to explain, with the best of my knowledge, what is known about automorphism groups in positive characteristics and how I tried to contribute to that myself. I will finish my talk then by proposing some open problems that I think are interesting related to what I prepared for you today. This is more or less the outline, so why don't we just start? And well, before we start with algebraic curves, just a couple of words about myself. my name is Maria Montanucci, as Luciane said, and as you can hear, I'm pretty much Italian, but I live in Denmark, and I got my PhD in 2019, and today I'm a very proud member of the section for mathematics at the Technical University of Denmark, and in particular, the Algebra Group. What is the Algebra Group? The Algebra Group is these nice faces you see in this slide, and they mean a lot to me. They are my second family. I spend every single day with them, every single coffee, every single lunch. And apart from myself, there is Professor Peter Belen, who is the head of the group, Anina Gruitsa, who is a postdoc. She doesn't work on algebraic curves, but more on rank metric codes and distributed storage and stuff like that. And we have two PhD students, Peter and I, and their names are Jonathan and Marie, and they work both on algebraic curves as much as we do. Well, this is actually everything about me, so why don't we just go to algebraic curves now? And well, in this talk, I will always denote with X a projective, geometrically irreducible algebraic curve defined over the algebraic closure of a finite field Fq. This algebraically closed field I will denote with either over line Fq or with K. And well, we all know what an algebraic curve is, right? It is an algebraic variety of dimension 1. So we have a collection of polynomials and zeros of those polynomials in some projective space over this algebraically closed field. And it is a very fundamental object, right? An algebraic curve. But the way in which we study algebraic curves today is not as old as one might think. We start, as far as I know, studying the geometry of algebraic curves in the way in which we do it today with Riemann, 1851, over the complex numbers. And as far as I know, the first time in which we start working modulo P, let's say, is only around 1924, so 100 years ago. And, well, the theory of algebraic curves has been the province of pure mathematicians for a long time, in fact. The turning point occurred around 1980, when Goppa found a way of using algebraic curves for error correction with the so-called AG codes. And that was a turning point because people understood a bit the versatility of algebraic curves as a tool, and since then, many applications can be found in applied mathematics. Very famous is elliptic curve cryptosystems, 1985, but nowadays you can find many, in fact, other applications available. So, we have our curve X defined in principle over an algebraically closed field when is a curve X defined over a finite field Fq. Well, a curve is defined over Fq when the defining polynomials of our curve as a variety have coefficients in Fq. And of course, as it always happens in mathematics, also between algebraic curves, we have a categorical morphism, what we call a rational map. So we have also an isomorphism, so a way of deciding whether two curves are essentially the same, right? And with that, it becomes relevant to study the properties of an algebraic curve that are invariant under isomorphism, the so-called birational invariants, in fact. And in this talk, I will focus on 5 such invariants. The first two are the genus G and the p-rank gamma of the curve. They are non-negative integers. The p-rank is actually between 0 and G. That is always the case. The set of rational points, x of Fq, invariant only, of course, with Fq rational morphisms. That is a set of points with coordinates in Fq itself, so not only over the algebraic closure as such. A bit more abstract, the Weierstrass semigroup at points of our curve, Hp. That is a numerical semigroup that you associate to a point of your curve and collects essentially pole orders of functions with poles only at P. And a bit more concrete, the automorphism group of your curve, which is, you can imagine, just a group of transformations of the projective space where the curve lives, permuting somehow the points of your curve, so with a faithful action on the points of the curve. These 5 objects will be protagonists of my talk, and it is very well known that, in fact, they reciprocally influence each other, and they influence the shape of your curve. And in this talk, I will try to explain what I know about the interaction of these 5 objects, and also how I tried myself to contribute to this picture through my research. Before I do that, let me mention one of the properties I probably like the most about algebraic curves, which is that an algebraic curve is a geometric object, right? It's a collection of points as such in a projective space. But in fact, an algebraic curve can be studied also in a purely algebraic sense by studying the twin brother, I would say, of an algebraic curve, which is what people call the algebraic function field of your curve. What is that? Well, in this slide, I present it essentially for a plane curve. So where, as you can see, we have only one polynomial defining the curve. And if you have your irreducible polynomial here, f, since it is irreducible, you could consider the quotient ring by the ideal generated by f. This object here is in fact a domain, because f is irreducible. So if we consider the ring of fractions of this domain, we get a field that we know theoretically. This field here is the algebraic function field of our curve. So the elements inside are rational functions, so formal ratio polynomials modulo f. And it's very nice because this algebraic function field is really a twin brother of your curve, in a sense that all properties you can study of your curve have a translation in purely algebraic settings in the algebraic function field. Even the points, right, of our curve, they become what people call places in the function field, so maximal ideals of discrete valuation rings, but also the categorical morphism between curves, the rational maps I mentioned before, they become field extensions. And also, all the birational invariants I proposed for you before in the previous slide, they have an analog in the function field setting. In particular, genus and p-rank, they become dimension of vector spaces of differentials in the function field. So they also have a translation there. And this is something I always liked, also as a student, about algebraic curves, because it is very versatile, right? You can approach a problem on algebraic curves either purely geometrically or purely algebraic, and you can switch between the two out of convenience based on which problem you are really studying. And I will do, most likely, that during the talk without realizing it. But yeah. But I mean, we are at a finite field conference, right? So what happens if we have a curve defined over a finite field? First question is, how many points does your curve have? And there is a very famous bound that was found by Hasse and Weil around 1940, which is the Hasse-Weil bound. It tells you that, in fact, a curve defined over fqx has at most q plus 1 plus 2g square root of q, many rational points. This is already a first interaction between two birational invariants, right? You can see a genus appearing here. So the genus has an impact on the number of points our curve can have. If the genus is small, we can't have many points. And the curve is called fq maximal if it attains the Hasse-Weil bound with equality. So we have the largest number of points we have according to this bound here. Do they always exist, maximal curves? Well, it depends, right? Because you can see a square root of q here. So of course, unless g is equal to 0, in which case you have a line, so you know everything is really known there, then you need to have that q is a square in order for this number to be the number of points of the curve. For this reason, since we want a field with square cardinality, you can see in the literature that people quite often talk about fq square maximal curves instead of fq maximal curves, just to emphasize that we need a field with square cardinality. And I will do that from now on. So when talking about maximal curves, my finite field of definition is going to be fq squared. So once we fix our finite field, fq squares, can you exhibit a maximal curve? Yes. And probably the most famous one is the Hermitian curve. Hermitian curve is given by a very nice plane model that you can see in this slide, and everything is known about this curve, I would say. The genus, q times q minus 1 over 2, is known. It is known to be maximal, which you can prove by hands by using the quotient, counting the points. And also the automorphism group is completely known. It is the projective general unitary group. The reason why this is probably the most famous maximal curve is multiple. First of all, it was proven by Iara and then later by Rook and Stishnot, we are in the 80s, 90s, that this value, q times q minus 1 over 2, is the largest genus that a maximal curve can have. And if you have a maximal curve that has this genus, then it is the Hermitian curve, up to isomorphism. So it really means that this curve maximizes the number of points, maximizes the genus, and it is unique with respect to this property. Not only, but this curve also has a very, very special geometry. The set of fq square rational points of this curve is what people call the classical unital. It is a set of points in the projective plane that is cut by lines in either 1 point, tangent line, or in exactly q plus 1 points. So there is nothing in between. Lines intersect in either 1 or q plus 1 points only. And Stishnot proved, we are around 1997, that this curve is also exceptionally nice. It has an exceptionally large automorphism group. Namely, if you have a curve that has more than genus to the 4th many automorphisms, your curve is this one again. So it's really the largest, if you want, automorphism group you can have. So now we have many interactions that we can see between the birational invariants, right? First, the genus has an impact on the number of points. Now we can see that if we have many points, the genus cannot be too large. This is an upper bound. And we can also see that if we have too many automorphisms with respect to the genus, we are a very specific curve, right? Let me also mention that, in fact, if we have a maximal curve, then it is known that its p-rank is 0. So there, this invariant assumes one value, simply, so even stronger relation, I would say. And, well, this is just an appetizer about birational invariants, but I will go back to it later during my talk. Now, you may wonder, okay, maximal curve, it has many points, why do you care about that, right? It depends who you ask. If you ask me, I would say, come on, they are rare, right? They are difficult to find. If you just shoot an arbitrary curve, it's not going to be maximal as such, right? So they are so difficult to find and intriguing, right? This is what I would say. But if you don't care about those things, then people cared about maximal curves because of the application to linear codes. In fact, I mean, we all know that when we want to construct a good NKD to linear code, then what we want to have is a large information rate, K over N, a large minimum distance, D over N, because we want to correct many errors with respect to the redundancy. And we also all know that these two numbers we want to make large actually are upper bounded. This is the singleton bound, right? So when people want to construct good error-correcting codes, they try to make these two numbers to be as close as possible to each other, that is to minimize the relative singleton defect, capital delta. What got paralyzed constructing codes from curves is that quite often these capital delta can be designed, can be upper bounded. And using Riemann-Roch theorem, for example, often one can obtain a bound like genus divided by the number of Fq rational points of the curve. And that is super nice, because if you want delta to be small, you might as well try to have the upper bound being small. So you might as well consider a curve that has many points with respect to the genus, right? And this is how maximal curves immediately appear, because we know they are the best from that point of view. So this is just an intuition on why these objects are interesting. This is more or less the background for my talk, right? Now let's go to some questions. First of all, if maximal curves are interesting, how do you construct them and classify them, particularly using the birational invariants I showed you before? Second of all, what can you say about the geometry of maximal curves? And there is many questions, in fact, that are still unsolved there. And I will propose you one question regarding Hermitian curves and their intersection in the projective plane. And lastly, what about the birational invariant automorphism group? What can you say there in positive characteristic? Let me start by the first question. So how do you classify maximal curves? And well, as I said before, maximal curves are rare. They are difficult to find in principle. But there is a machinery that people use in the literature for many, many years to construct them. And this machinery was developed by Kleiman and Serre around 1987. It works as follows. So what they proved is that if you know a curve x that is Fq squared maximal, and if y is another curve that is covered by x, I will explain what being covered means, then y is maximal as well. What does it mean to be covered? Well, y is said to be covered by x if y is the image of a rational map, non-constant rational map, with domain x. Imagine you have x, you have a rational map that has x as a domain, y is the image of this map. So this really means that if you know a maximal curve, then you can start constructing rational maps, and the image will give you for free a maximal curve. There is a construction, a special type of covering that people studied a lot in the literature, that is the so-called Galois coverings. They are a subclass of coverings of curves. And they are very nice because, as the name suggests, Galois, they are related to automorphism groups. And in fact, a way to construct Galois coverings is as follows. Once you have your curve x, then consider an automorphism group on x. This automorphism group will act on the point of your curve. It will have some orbits. If you treat these orbits as one point each, then you give rise to another curve that is Galois covered, as one says, by x. This is the intuition of the definition. Really, if I want to be very formal, then I will have to look at the function fields. And in fact, y is Galois covered by x when the two function fields of the curve are related as fields by a Galois extension. that is the real definition. But this really means that if we know a maximal curve that has many automorphisms, this allows you to create many maximal curves. And we know one. The Hermitian curve I mentioned before for you has a very large automorphism group, as we commented. And for this reason, for many, many years, people constructed maximal curves in this way. They took the Hermitian curve, an automorphism group, and then they created a Galois coda. And they even conjectured that every maximal curve arises in this way. So it is either covered or Galois covered by the Hermitian curve. This conjecture is false, now we know, but the first counterexample is not that old. It's from 2009. Was found by Giulietti and Korczmaros with the GK curve, as we call it. And for me, this is pure magic. I never understood why it works, particularly because, think with me, you want to find a maximal curve not covered by the Hermitian, so are related to the Hermitian. What do? You create a space curve, so two equations, and one is the Hermitian. So one equation is the Hermitian curve. And as you can see, they took the Hermitian curve and they added the Z coordinate. So somehow they lifted the Hermitian curve to the space, right? They gave to the points a Z coordinate. And even though they lifted the Hermitian curve to the space in this way, this curve is not Fq square maximal, like the Hermitian is. It's Fq to the 6 maximal. So they needed a cubic extension of the field to find maximality. And there, this curve is not covered by the corresponding Hermitian curve. So the Fq to the 6 maximal 1. And what I like even more about this curve with this magic of lifting the points of the Hermitian is that they even lifted all the automorphisms of the Hermitian. In fact, the GK curve has a very large automorphism group of order genus squared, more or less. As you can imagine, this curve attracted a lot of attention in the literature, and many questions arise naturally. The first one that you can see here, question 1, why did they need to go to a cubic extension to find maximality? I mean, to have a maximal curve, I need a square, as we commented before. Why a cube? So the question would be, can you find an Fq to the 2n maximal GK curve when n is just odd, not 3, odd? Second question, since you defined birational invariants before, can you use them for something related to maximal curve, to construct or to classify maximal curves? Last question, if you want to understand the magic of this curve, why don't you look at curves with roughly genus square, many automorphisms? Because you will find it there. This curve has G square many automorphisms. So why not try to understand the magic from the automorphism group point of view? Let me start by question 1 by telling you that, in fact, an Fq to the 2n maximal version of the GK curve is known. And it was found only 1 year after, in 2010, by Garcia, Guneri, and Stichtnot with the GGS curves. What the authors did fixing n odd was very simple. As you can see, the GGS curve Cn looks a lot like the GK curve. The only thing they did was to change the degree of z here from q cubed plus 1 to q to the n plus 1. So if n is 3, this is the GK curve. But in principle, we have an infinite family, right? Fq to the 2n maximal. In my master degree thesis with Massimo Giulietti and Giovanni Zini, I proved that the curve Cn is not covered by the Hermitian curve, so it shares this property with the GK, but as far as I know, it is still an open problem to understand if these curves are covered, not necessarily Galois, by the Hermitian curve. And actually, 8 years after, together with Peter Behlen, we found another generalization of the GK curve. The BM curve xn that you find here is a lot uglier, as you can see equation-wise. It is still Fq to the 2n maximal, where n is odd, exactly like the curve Cn. And the reason why our generalization looks uglier is because we didn't try to generalize the model of the GK curve, but we tried to generalize lifting many automorphisms from the Hermitian curve. What we obtained, in fact, with the curve xn is an infinite family of maximal curves, generalizing the GK curve in the sense that x3, so n equal to 3, gives you something isomorphic to the GK curve. These curves are not Galois covered by the Hermitian curve as well, and they have a pretty large automorphism group again, roughly genus squared many. And this was super important for us, because the curve xn and the curve Cn have the same genus. And this is scary, right? Because it is a birational invariant. So in principle, they could be isomorphic, the two generalizations. But in fact, they are not, unless they are both the GK curve. So the case n is 3. And why is that? Because we forced the curve xn to have a different automorphism group. So one birational invariant is failing. They can't be isomorphic. And I'm very proud of this result. It was probably the most important one in my career, and also because it allowed me to think about other problems afterwards. And in 2025, with Tobias Struhe, Peter Behlen, and Giovanni Zini, we have been thinking about the following. I mean, we have the GK curve, right? It was generalized in two ways. First, 1 year later, by Garcia-Guneri-Stirnot, and then we have an 8 years gap, and the BM curve was created, right? You can imagine that from the GGS curve, many constructions arise, error-correcting codes, and also other maximal curves, considering subcovers. But the curve Cn is not that different than the curve Xn. They have the same genus. So why don't we try to find the twin brothers of all these constructions, but under the BM curve? So why don't we try to emulate all the construction that has been done for the GGS curve, but on the BM level? Because maybe this was our idea. For these constructions, we can force them to have the same genus, like it happened for Cn and Xn, but a different automorphism group. So why don't we try to replicate the difference between these two curves at the level, for example, of subcovers? Because in this way, we can create eventually new maximal curves for free. That is the idea. And in fact, in 2025, we decided to work in this direction, and our inspiration came from a paper by Tafazolian, Terán Herrera, and Torres from 2016, where the authors consider some very clever Galois subcovers of the GGS curve that allowed them to create new maximal curves not covered by their mission. In their paper, the authors have two families of such subcovers of the GGS curve, and here I propose you only one, Y and S, which is a subcover because they simply changed from the GGS curve the degree of Z. They took a divisor of the degree. This gives you a Galois subcover, and the nice thing about those is that they are maximal, because they are covered by a maximal curve, so I can use Kleiman's there, but they have a very strange value of the genus. So strange that they could use it to prove that these curves are often not covered by the mission curve, so new. So our idea was, okay, why don't we try to find a Y tilde? So a curve like Y with the same genus, but has a Galois subcover of the BM curve, because if you are very lucky, it will have a different automorphism group. So we can use that birational invariant to say, look, the curve Y tilde I just found is not isomorphic to the curve Y, it is new. As you can imagine, to have that working, first we need to compute the automorphism group of Y, because I want to use it to distinguish it from Y tilde, then we have to find Y tilde, and then we have to find the automorphism group of Y tilde. And computing the automorphism group of Y was something we did actually the year before with Guillermo Tiziotti and Giovanni Zini, using the birational invariant I didn't talk that much yet about, Weierstrass semigroups. In fact, I said that Weierstrass semigroup is kind of, a numerical semigroup that you can associate to points of your curve. It is invariant under isomorphism, but of course then it is also invariant under automorphism. So this really means that if you pick 2 points from your curve and you have an automorphism mapping the point P to the point Q, then these 2 points have the same Weierstrass semigroup. Vice versa, if you compute a lot of Weierstrass semigroups, right, and you find many different ones, it means that these points cannot be mapped to each other by an automorphism. So they need to be in different orbits. So what I'm trying to say is that Weierstrass semigroups can be used to predict the orbits of automorphism groups. And in this case, so what we did, in fact, for the curve Y was to compute a lot of Weierstrass semigroups, and we realized that there was one point that was just different from all the other, a different Weierstrass semigroup. This means that the automorphism group needs to fix it, and this is such a strong condition, such a strong constraint, that it allows you to determine the automorphism group explicitly, completely, which is how this result essentially was obtained. Okay, but now we know the automorphism group of Y, let's find Y tilde. And surprisingly enough, what we had to do was simply the same as they did. We took the BM curve and we reduced the degree of Z in the exact same way. In this way, we could prove that this curve is maximal. Again, this was for free because it is covered by a maximal curve, so Kleiman's error applies. It has the same genus of the curve Y, so we could recycle, let's say, the proof of the fact that they are not covered by their mission from the previous paper. And then we started computing Weierstrass semigroups in this curve. And this time, there was not a special point. And this allowed the automorphism group to be larger, in fact, than it was before. And in fact, this means that the curve y tilde and the curve y cannot be isomorphic because the birational invariance automorphism group fails to be the same. This is more or less what we did in this paper. I would like to mention that there is also another family of curves in the same paper from 2016 that the authors constructed, and we generalized that too. But I didn't propose it for you today because the intuition is in fact exactly the same as the one in y tilde. This was kind of an application on how to use birational invariance somehow to construct, to some extent, maximal curves, but can you use them to classify maximal curves? And together with Peter Balen, Jonathan Neeman, and Luciane Kuos, we have been investigating this question in 2024 by considering a family, very large family of maximal curves, which is the curve CI that you can see in this slide, that were constructed by Garcia, Stittner, and Ching in 2000 as Galois subcovers of the Hermitian curve. The authors, in fact, knew that the curves CI are maximal because they are covered by the Hermitian, but they didn't know how to distinguish them up to isomorphism. So how many non-isomorphic curves of type CI do we have in this family? This was the question. And in our joint work, we managed to compute the number of isomorphism classes exactly there. And they are infinitely many curves because I here is just an integer in principle. Why did we choose to test, the use of birational invariance? Why did we choose this family of curves here? The reason is because birational invariants there fail a lot to distinguish them. I mentioned 5 birational invariants, right, so far. For the curves CI, we knew that they all have the same genus to start with, so we couldn't use that to distinguish them. So they have the same number of rational points because they're all maximal, right? Same genus, so we can't use that either. They all have the same P rank because they are maximal, and we said P rank is 0 for maximal curves, so we can't use that either. So we said, okay, maybe I can use the automorphism group. No, you can't, because we computed it, and for every I, the automorphism group has the same order, the same structure, the same action. And then we were a bit disappointed, because it was, we computed the automorphism group, and we can't even use it. And that is not true. In fact, the automorphism group has a very peculiar action. It has an orbit with 4 points only, and this is the only orbit of that length. So there is 4 special points that each of these curves has. So the idea was, okay, let's assume for a second that we do have, between a curve Ci and Ci prime in the family, we do have an isomorphism. Well, then since the automorphism groups need to match, and the actions need to match, the 4 special points of the curve Ci need to be mapped to the corresponding 4 special points of the curve Ci prime. And then, okay, but if this is the case, the Weierstrass semigroups at those 4 points need to be equal to the Weierstrass semigroups at those 4 points. So we computed them for every I. And if we have an I and I prime for which these 4 Weierstrass semigroups are not equal to those 4, and then they can't be isomorphic, because the birational invariant is failing. You may wonder, okay, what if they are equal, right? If they are equal, I can decide explicitly where I'm mapping 4 points to which 4 points. And this is a very strong constraint. So strong that it allows you to find the isomorphism exactly by hands between the 2 curves. So what I'm trying to say is that if the Weierstrass semigroups at the 4 points are not matching, the curves are not isomorphic, but if they do, we could construct the isomorphism explicitly. And this is why we could count the isomorphism classes precisely. Maximal curves, right? What about the geometry? My second question for you today. They are known to have a beautiful geometry. There is a result that is called natural embedding theorem from Korczmarov and Torres, who tells that every maximal curve is up to isomorphism contained into an Hermitian variety as a non-singular curve of the VQ plus 1. I mean, very strong conditions, right? But in fact, even for the most famous maximal curve, the Hermitian curve, a lot of geometric questions can be found that are very natural but still unanswered. And the one I have for you today is a question that actually an Indian mathematician, Mrunmayee Datta, proposed to me when he visited DTU last year. And I have the question in the slide for you, I'm gonna read it. It says the following. Imagine you have your Hermitian curve in the plane, and consider any other curve, irreducible, curve D of degree small d. Is it possible that your Hermitian curve and the curve D intersect in exactly d times q plus 1 rational points? distinct rational points. When he asked me this question, I said, this is known. This is definitely known. It's such a fundamental question, right? And he was interested because he was trying to compute the weight of some code words in some code. I mean, he was coming from a coding theory reasoning. But as a geometric question, for me, was so natural that it must be known. And of course, the question as such makes sense, because if you know Bezout's theorem, right, our curve, Hermitian curve, and the curve of degree d intersect in d times q plus 1 points, counted with multiplicity, over the algebraic closure of the finite field of definition. So we have this as an upper bound, I would say for free, but nobody tells you that the points are rational, neither that they are distinct. And then I started studying the literature to realize if it was really unknown, the answer to this question, and I realized that it was known only for the case d is 2, so if you have a conic. And the answer was given by Donati, Korchmaros, and Durante in 2009. I said, why not? Let's try to investigate this question. And a computer search immediately showed that if you choose Q and D too small, the answer is negative, but the intuition was that it must be true, let's say, for larger values of D. And in our joint work in 2024, with Peter Bellem, Rimo Idatta, and Jonathan Niemann, we managed to answer this question for large values of D, between Q plus 1 and Q squared minus Q. For larger value, it becomes trivial, the answer, and partially for smaller values of D, which I will show you in a minute. And I would like to give you an intuition on how we solve this question here for large values of D and for small values of D, and the techniques are different in the two cases. So if you imagine that the answer is true, and you want to prove that the answer is true, then you have to construct the curve D. How do you do that? This is what we did for large values of D. So we consider first our emission curve, and then a set of values in Fq squared that I called capital S here. This set here of values from Fq squared B has cardinality Q squared minus Q. That is obvious. But the reason of interest for us is that one can prove by hands that all the lines determined by those B with this shape, they are not tangent lines to their emission. And hence, as we remember, we either have a tangent or we intersect in Q plus 1 points, right? As we said before. So all these lines are intersecting in Q plus 1 points, the emission curve. So it is tempting, since each line has Q plus 1 points, it is tempting to just take D of them, right? To get D times Q plus 1 points. In fact, we multiplied D such lines, and then we took a linear combination with the quotient of the emission curve itself. Because in fact, this implies that we have D times Q plus 1 points, Q plus 1 per each line, D lines, that make both this part here to vanish, and of course, this part here to vanish, because this is just the emission curve. So this means that this curve here has degree D, because remember that D is larger than Q plus 1, and the quotient of the emission is Q plus 1, and we have D times Q plus 1 rational points in common with the emission curve. You might say, are you sure that you have exactly D times Q plus 1 points? The answer is yes, because these curves, in fact, don't intersect at the emission curve. These lines all intersect at the same point, 1, 0, 0, which is external to the emission curve. So you have to imagine you have this external point, then you have these D lines, and each contain Q plus 1 distinct points. At this point, all we had to do was to prove that this curve here is irreducible, and this is where the constant alpha comes into the game. We proved that there exists an alpha such that this curve is irreducible. And this is how we answered this question. As you can imagine, this strategy, which is very, very simple, very intuitive, doesn't work if D is small, because I'm using strongly that D is at least Q plus 1 to have a curve of degree D here, right? So what do you do if D is small? If D is small, namely for these three, we could answer completely this problem, but also for these 4 partially and other small values of D, what we did was first to change the model of the emission curve in a model of this type. It is the same up to isomorphism. And then we looked at curve D of this shape here this time. The reason for that is that if you try to compute the intersection points of these two curves, you see immediately that they don't intersect at infinity. So if z is equal to 0, so you're looking at affine solutions, and the affine solutions are exactly the x and y that satisfy, say, these two equations simultaneously. But this equation here, x equal to alpha y to the d, allows you, if you plug it in here, to remove x. So you get one equation only in y. You get a univariate polynomial. And it is exactly this univariate polynomial. So what do you want to get? You want to get that this polynomial has exactly d to q plus 1 solutions, all in Fq squared. In other words, you want to understand what is the splitting field of this polynomial. And if we can find an alpha such that the splitting field is Fq squared, then we answer the question. And this is exactly what we need in this case. I would like to emphasize that, again, DS3 now is completely solved, but in general, we don't have a full solution for this problem. It's still open. I would like to finish my talk just by mentioning a few things about automorphism groups, so this other birational invariant, and what is known there, what is the interaction with automorphism groups and the other birational invariants. A lot is known. For example, several authors proved that if you have a curve of genus at least 2, then the automorphism group is finite. So this is already a strong interaction, and in fact, if the genus is 1 or 0, so you have an elliptic curve or a line, then the automorphism group is infinite in that case. What I like the most, I would say, about automorphism groups in positive characteristic is that very strange behaviors can happen that you cannot find in characteristic 0. In characteristic 0, it is very well known that something like the classical Ritz bound holds. So your curve is going to have always, at most, 84 times g minus 1 automorphisms. So something linear, right, with respect to the genus, not that large. And this bound is attained. There is many Hurwitz curves available. The Klein quartic is probably the most famous one. It has exactly 84 times g minus 1 automorphisms. This bound, we know, fails in positive characteristic, and this is what makes it intriguing, right? And we know that because I showed you before the emission curve. Emission curve has genus to the 4th, many automorphisms, so far away from being linear, right? And this means that if we want to understand automorphism groups and their magnitudes, then we know everything if the automorphism group has size larger than genus to the 4th. After this result, people started to think, okay, what happens if I have genus to the 3 many automorphisms? Can you tell me which curve I have in my hands? What happens if I have genus squared? So on and so forth, right? And Hem, in his PhD thesis, we are only 3 years after, managed to classify completely curves with more than genus to the 3 many automorphisms. He proved that your curve in this case is exactly one of these 4. And all these examples here, the emission is there, right? We expected it. It has more than genus to the 4th, so particularly more than genus to the cube. All these curves here have p rank 0. So like having many rational points implies we have p rank 0, having many automorphisms also implies having p rank 0, which is very, very beautiful, I think. So far we know everything about automorphisms if we have at least genus many. So we have an interaction between genus and automorphism group. What about the p rank? The person who studied the interaction between automorphism groups and p rank was Nakajima, 1987, and he proved a chain of very, very beautiful results. He proved, among other things, that the p rank of your curve has an impact on the size of p groups of automorphisms, where p is the characteristic of the ground field of definition. And also he proved that if you have too many p elements, let's say with respect to the genus, the p rank is 0 again. So we go back to that class of curves. It proves also that vice versa, if your curve is very far away from satisfying these, it is ordinary, it has p rank the largest possible, then the automorphism group is small. It has order at most 84 times g squared minus g. This was the very first paper I studied in my PhD about automorphism groups, and I had many natural questions while studying it. First of all, this is nice because it tells you something about bounds for p groups of automorphisms, but what about d groups, where d is another prime, not p? What can you say there, right? Can you find a bound that is as nice as this one and prove maybe that it is sharp? Why didn't Nakajima exhibit extremal examples for this bound? It is because you can improve it maybe to make it sharp. This was another natural question. Lastly, we know everything if we have at least cubic many automorphisms. We don't understand the GK curve that has roughly genus squared automorphisms. So what can we say if we have a curve that has more than genus squared many automorphisms? What can we say there? Are they enough to ensure that my curve has p rank 0, or do I need to go to Hans classification and have at least cubic many? These were some natural questions that I had while I was a PhD. And let me just mention what I managed to obtain by studying these problems. And first of all, what can you say about D groups of automorphisms, D and E other prime? First thing first, it made sense to study this question because we knew that Nakajima's bound, if D is P, couldn't be improved. There is many authors constructing, in the literature you can find, constructing Nakajima extremal curves. So curves attaining Nakajima's bound. So we know that that bound could be improved, for example. But in the case in which D is not P, we realized that there was already a result by Zomorodian from 1985 in characteristic 0, answering our question. Zomorodian, in fact, proved that in characteristic 0, your D group has order at most 9 times G minus 1. And of course, this bound can be attained only if D is 3, right? Because if G is a D group, then to have order divisible by 9, I need to have D is 3. What Gabor Kočmaroš and myself managed to do in 2020 was not only to prove Zomorodian's result in positive characteristic, as you can see in this bound here, but actually we managed to improve it if D is larger than 3, obtaining a bound that is a bit better than 9 here. And this improvement was nice because, in fact, our bound, if D is larger than 3, is sharp. If you consider the Fermat curve of degree D, D is your prime, then this curve has an automorphism group of order D squared that you can find by hand, and this square is exactly what you get if you plug in the genus of that curve in the bound. So we obtain the bound if D is larger than 3, that is sharp, in fact. So our problem then became, okay, you proved Zomorodian's result, but is this bound sharp? Can you exhibit extremal curves with respect to your bound? To understand that, we studied a lot of literature about 3 groups, finite 3 groups, and we managed to prove first that if you have an extremal group G with respect to our bound, 9 times G minus 1, you can tell me exactly how your group looks like in terms of generators and relations. And this was nice because we used this classification to think about how do you construct an extremal curve with respect to your bound. And our idea was to start with an elliptic curve. It has an infinite automorphism group, so you have plenty to choose from, and lift those automorphisms to a space curve, so a curve of largest genus, because if you choose it correctly, you can lift a lot of automorphisms. And in this way, we managed to prove that you can always find an extremal curve with respect to our bound for every possible value of the genus. And it is an algorithm, the one we developed. So if you use magma, for example, you can even find explicit equations for these extremal curves. And we could also prove that, in fact, all the 4 cases listed here really occur, because we could construct curves having those. I would like to finish my talk just by mentioning what can you say about improving Nakajima's result for ordinary curves, so where the P rank is very, very large and where there were not extremal examples. We studied this problem in odd characteristic with Gabor Kočmaroš and in even characteristic with Pietro Speziali, and we managed, in fact, to improve Nakajima's bound, but for solvable automorphism groups of ordinary curves. Our bound reads something like, if you have a solvable automorphism group of an ordinary curve, then its order is at most genus to the 3 over 2. So better than G squared, which is what Nakajima had. And in fact, this bound is sharp now. And working with Pietro Speziali, Gabor Kočmaroš, and Giovanni Zini, we found extremal curves with respect to our bound, which is what we called generalized Artin-Mumford curves. So this bound here now cannot be improved. However, we have an assumption. This is only for solvable groups, so you may wonder, what can you say if your group is not solvable? We studied a bit this problem with Pietro Speziali. We obtained a lot uglier bound, as you can see, and in fact, we don't have extremal examples. And in fact, this makes us think that maybe this is not an optimal bound, who knows, but it is still an open problem, in fact, to solve completely for the non-solvable case, this problem. So to find a bound that is sharp for automorphism groups of ordinary curves. Lastly, what can we say, as I mentioned before, about automorphism groups of order G squared? This is a problem that I studied in 2023, and the reason why I decided to do that, trying to improve Hans' results, is that I realized that if you have more than linear automorphism groups for your curve, then you can say really a lot about the action of your automorphism group. It was already known that if you have quadratic many if you have more than linear, pardon, many automorphisms, then your group cannot act freely on the curve. There is only 4 cases that can occur. So my idea was, okay, if I assume that I have at least genus square many automorphisms, then I can assume that one of these cases occur, and then see what happens. So kind of proceed with a case-by-case analysis. By doing that, I realized that a quadratic bound was very simple to find in the first 2 cases, and in fact it was known, which means that if I have more than genus square automorphisms, these 2 cases are irrelevant for me. And all the curves that Hen found, if I have at least cubic many automorphisms, fall into case 4. So this makes me think that probably a quadratic bound is possible to find also in case 3, which would be very nice because it really means that if you have more than quadratic many automorphisms, then you can tell me exactly how the group is acting. Case 4 needs to happen. And this is the result that I got in 2023. In this investigation, I proved, in fact, that in case 3, there is a quadratic bound, which really means that now at least we know if we have quadratic many automorphisms, then our group is acting in one very specific way. If you remember, the aim was also to try to understand if having many quadratic many automorphisms would be enough to have P rank 0, and that I didn't manage yet. I could prove that it is the case if some extra assumptions occur, if I have even genus, or if I know something about the stabilizer of 2 points. But again, this is still an open problem to understand if quadratic many automorphisms are already enough to have P rank 0 or not. Is it doable to, create a list of all possible algebraic curves having genus square many automorphisms? Maybe, but it would be a lot more difficult than what Hen got in his PhD thesis. The reason being that there is already many examples in the literature of curves with roughly genus square many automorphisms. The GK curve I showed you before is one example, but there is also scabulant curves, as we proved with Giulietti, Kuos, and Zini. They also have genus square many automorphisms, and they satisfy, in fact, case 4 I showed you before, among others. So it is still an open problem to improve Hen's results, having a list of curves satisfying those, the assumptions, but it would be very difficult. This is my intuition, at least. Let me finish my talk by just proposing you some open problems that I think would be interesting. The first one, kind of a dream for me, would be to understand how large can be an unsolvable automorphism group of an ordinary curve. Can you find a sharp bound there? Another question would be, what can we say about curves with genus square many automorphisms? Can you give me a list of such curves? Can you prove that they all have P rank 0? Can you even aim to classify maximal curves based on their automorphisms? How does the automorphism group of a maximal curve look like? Lastly, can you link automorphism groups with other birational invariants of a curve? For example, the one called A number that is not well known, well studied in the literature, I feel. These are just some open problems I wanted to finish my talk with. And yeah, I've been talking enough, I suppose. So thank you so much for your attention.
So thank you for your very nice talk and a lot of problems for people who solve. So questions, comments? Yeah. Daniel?
So thank you very much for the beautiful talk. So I just would like to ask you something about slide 21. Just curiosity. 21. Oh yeah, yes. So here you say that there exists alpha in Fq squared.
Yeah.
Did you also, because I think that you used something about Galois theory in order, yeah. So does this also tell you the number and a lower bound on the number of alpha, giving you something irreducible? I mean, okay, for your purposes, it was okay to prove the existence of one alpha, but did you get also some constraints on the lower bound on this alpha?
I didn't try to count them, but of course we have, algebraic conditions for alpha. So I think it would be possible to count them somehow, or to estimate the number of alphas that would work. I didn't try, but I believe it could be doable.
So no, just to know if they are rare or not, like
Just to know, pardon?
if they are rare or not. The
Yeah, no,
irreducible curves of this shape, just a curiosity. Okay.
I don't have an intuition for it. I didn't try to count them. But yeah,
Okay.
I would say they are probably rare.
Okay, thank you.
Hi, thank you for the talk. Just one other curiosity of your bound with Pietro Speziali of G to the 7/4 times a constant, say, for ordinary curve, right? Is there any difference or any claimed difference for sharper bounds between even and odd characteristic? Can you expand and say something on?
We didn't analyze the even characteristic case, right? We have an assumption.
Oh,
here
sorry,
that-
sorry, I'm sorry. So this is for odd characteristic. Anything for maybe larger or something, but smaller than G squared for the even characteristic in mind?
We didn't investigate it because we got very much, focused on trying to obtain a sharp bound in our assumptions here, right? We didn't manage, in fact, but I don't have an intuition for it. Many of the techniques we use fail simply immediately.
Okay, thank you very much for all the talk.
You have this you have just one maximal curve of genus QQ marathon over 2. You also have just one maximal curve for the second genus and third largest genus.
It is not known for the third one, right?
For second, yeah.
For the second, it is.
Yeah. For the third, okay. For the third, not yet.
Oh.
But do you expect that we could have a bound for the number of maximal curves of certain genus?
I mean, you can imagine that if the genome becomes smaller and smaller, then you have plenty, right?
Yeah, but if you go to the if you go to genus 0, then you have just one again. So
That is also
actually,
true.
the genus goes a little bit. I don't know.
No, genus 0 is a bit special.
Yeah.
Yeah.
Okay.
Yeah. No.
Okay, let's just think.
Thank you very much.
Now we have a coffee break.
Just to remind you guys, so now we have our coffee break with the hall of the building right behind us, Professor Loebel's hyperspace. And let me just remind you that after coffee break we will have our parallel sessions. So make sure you want to come back to this room or go into the other building. And I would kindly ask you not to go. I mean, during the contributor talks, please do not go beyond 20 minutes, so that you can keep our synchronization. So people will be moving back and forth from one building to the other. So I kindly ask you not to go beyond the 20 minutes, so that people can ask a question and then move to the other building. Thank you. So we'll go to the coffee break now.
my mobile. Oops.
We are going to start the second talk of the day. And so it's a pleasure to introduce Giovanni Zini. And he's going to talk for us about double Artin-Schreier extensions of rational curves. Thank you, Giovanni.
Thank you, Luciana. And thanks, of course, to the organizers for giving us the opportunity of being here in São Carlos. And thank you to you for being physically here these 20 minutes. Let's try to keep them short. I'll just try to show something that we played with and some hopefully funny examples in order maybe to catch your interest for future thoughts or reasonings on it. And these plays, were made together with Heriberto Borges. So once again, thanks to him, not only for the organizing, but also for collaborating. And Jonathan Tilling-Niemann, the PhD student of Maria that she showed before. Okay, the fields we are considering, I'll try to skip everything that Maria already introduced before. So we are working over the closure of a finite field, over the Q and characteristic P. And we consider curves, meaning projective curves and absolutely reducible ones. If you want non-singular, if you want to have the closest connection between places and points. Again, we can think equivalently to the function field of the curve. The curve will be also be defined over Fq, so we can consider the function field with constant field Fq instead of K, the closure. And out of X will denote the group, the whole group of all automorphisms over K, over the closure of the curve X, acting faithfully on the points, say non-singular points, or equivalently the K automorphisms of the function field. And we'll also use genus and P rank of the curve as defined and as used and showed before in the previous plenary talk. We will consider coverings between curves. So X covers Y means simply that there is a rational dominant map from X to Y. that is equivalently that the function field of the underlying curve is a subfield of the function field of the curve above. In particular, we're interested in Galois coverings, where the function field extensions is a Galois extension with Galois group G. Notice that the degree of the rational map is exactly the size, the finite size of the group G. Well, when we have a Galois covering X to Y realized by a group G, then we can inherit on the curve Y automorphisms from above, in the sense that the normalizer of G in the whole automorphism group of X, section over quotiented over G, acts as an automorphism group of the curve Y. You can see this, of course, on the function fields, since the normalizer acts on the fixed points of G, which is precisely the function field of Y, or you can see it geometrically as action on the G orbits on X. Well, vice versa, if you have an automorphism group on Y, we say that we lift it to X if we can inherit this group H from an automorphism group above, which is made by the Galois group G, normalized by a copy of H tilde, say. So in this way, we say that H is lifted to X. Please notice that having a section isomorphic to H in general doesn't imply that we have a subgroup isomorphic to H above. This is obvious in group theory. Okay, so we usually say that the group is lifted if we have a copy of H above, okay? Not just a section of H. Yeah, not just a section isomorphic to H. Okay, and actually, we can, and in the literature, actually, this was made to construct new interesting curves somehow in order to lift automorphisms that we have on our favorite curves. Just some examples that, again, were already showed before. We can start from the Hermitian curve in this norm trace equation and construct the GK curve as this Kummer extension. And in fact, we can lift, or at least always a section, but often actually to lift, the whole group of the Hermitian curve, the PGU3Q, to an automorphism group, and actually to get all automorphisms of the GK. This was generalized, as we heard before, to Garcia-Guneri-Stichtenot curves. In this case, we lift from the Hermitian not the whole group, PGU3Q, but a large subgroup of it. Actually, the one-point stabilizer, which is a maximal group because the group is PGU is primitive. Actually, it is too transitive actually on the rational points. And starting from a different model of the Hermitian curve, we have a covering curve named after Belen and Montanucci, to which we lift another large automorphism group from the Hermitian, namely the maximal subgroup of PGU3Q stabilizing Q+1 rational collinear points. Okay? These were examples as Kummer extension. But we can, of course, see in this setting also easier examples, single equations. You know, the Suzuki curve as extension of the rational function field in X, you see, as an Artin-Schreier extension. In fact, in this case, forget the exact definition of the automorphisms, but we can lift to the Suzuki curve all the automorphisms of the line in X, fixing one point, the point at infinity. And indeed, what we get in this way is the whole one-point stabilizer on the Suzuki, okay? Which is actually not the whole automorphism group of the Suzuki. We know that
the Suzuki group is much larger, but still is a large automorphism of it. It is a maximal subgroup, the one-point stabilizer indeed. And we can see in this way also the recurve as a double Artin-Schreier over the rational function field in X, in characteristic 3, as you know. And indeed, in the very same way, very, very similar, you can consider the automorphisms of the line in X stabilizing infinity and lift them naturally to the recurve. And once again, what we get in this way is the whole one-point stabilizer of, say, P infinity in the automorphisms of the recurve, which is, again, a maximal subgroup of the famous simple regroup. Notice that, let me notice that such semi-direct products, that is the Galois group, the elementary abelian Galois group of this extension, semi-direct, the lifted group, are indeed semi-direct and not direct. Why I say so? Because somehow they are more interesting than just, say, take separate variables, take invariants of two groups, and give automorphism acting separately on one variable and on the other, okay? Because if you perform such constructions, which are of course interesting for other reasons, you get, of course, direct products of group, okay? If you act separately on different variables. This is not the case for such semi-direct products. Well, the recurve, we can write it simply in this way by finding a plane model in UV of the rational curve in X. You see, we have this curve, which is rational. Actually, the function field is Kx, is the same of X. And the recurve is constructing in this way. You replace the plane coordinates, u and b, with y to the q minus y and z to the q minus z, okay? And the plane curve C is rational, has genus 0. And we can be inspired by such examples or others that I will show to play as follows. Take curves constructed as double Artin-Schreiers of this shape. The polynomials are the ones defining Fq, so y to the q minus y and z to the q minus z, over rational, plain, possibly easy curves, okay? And see what happens. Well, the goal is to obtain interesting curves of this shape X, to lift many automorphisms from the rational curve below, from the plane rational curve, and possibly to obtain large automorphism groups above. Large in the sense of what Maria explained before, so with respect to the other birational invariants, one for all with respect to the genus of the curve X. So easier plane curves with genus 0, irreducible conics. So what we did actually, and I will not go into details not to bother you, we performed quite a large study and throughout study of curves of this shape over general conics. Let me say in this way. General in the sense of being defined over Fq, or maybe over a closed extension field of Fq. But say, for instance, take any conic over Fq, C, and study genus P-rank lifted automorphisms. Of course, if you take a very generic conic, you cannot expect to say everything of this on this curve, okay? But still, you can try to perform a general study using Artin-Schreier theory and other stuff, and say properties of this kind. Genus, P-rank, lifted automorphisms. Here, I will just show some remarkable examples in the next slides. Okay. Okay, let me just mention the crucial point, which is very, very easy. That is, when we have an automorphism group of the rational curve of the conic below, which is defined over Fq, and acts on the line at infinity as a subgroup of PGL3Q, that is projectivities of the plane, because you know the automorphism group of the conic is in fact projective, is inside the PGL3Q. So we take affinities, say, affine maps, invertible maps defined over Fq, and we can lift them very easily for free somehow, because the polynomials, the Artin-Schreier extension are made in order to extend, to lift these maps to the curve X. I described here how to do this, but it is very, very easy actually, because you can take the linear part defined over Fq with the coefficients A, B, C, D, and use the same coefficients to define automorphisms on Y and Z, and then translate in order to fix the rest. Okay? Example. Start with the easiest possible parabola, V equal U square. For simplicity, take P odd, just for this presentation. Well, the structure at infinity of the conic below gives to you the P rank, and here also the genus. This is a curve of P rank 0 and genus Q square minus Q over 2. You can guess some interesting curves already with these properties. We can lift, as I said, the whole one point at infinity stabilizer over Fq, which has size Q times Q minus 1, and it is a maximal subgroup of PGL2Q. So we are able to lift a maximal subgroup, one of the biggest one, actually the biggest one, proper maximal subgroup of PGL2Q. And in this case, just in this case, we are also able to show that what we get, Galois group and Lifty subgroup as a complement, is the whole automorphism group above. Actually, it was not us showing that this is the whole automorphism group, because up to changing the model, this is the so-called Homakim curve with this equation, which has a number of interesting properties. For instance, it is the unique smooth plane curve attaining the cycli bound on the number of rational points and so on. Well, another example with parabolas. Here, I cheat a little bit in the sense that the parabola is not defined over Fq, but over Fq squared, because I'm adding that epsilon with a trace 0. Well, in this case, okay, this part is the very same, but the point is that the curve that we obtain is the Hermitian curve, the classical one, okay, with a suitable change of variables. And so, you see, we know, Maria recalled us, that we have many automorphisms with respect to the genus, actually the largest size that we can have. And notice that the examples that I gave to you up to this point, and I should also finish maybe in a few minutes, have all P rank 0. In P rank 0, there are some upper bounds, as we heard before, but there are much lower upper bounds for the size of the automorphism groups if we have ordinary curves. And this is the case if we put as conic the easy hyperbola u times v equal 1. Well, in this case, it is obvious that the curve that we get is the Artin-Mumford curve of this shape, which is ordinary of genus and P rank Q minus 1 square, has two points, distinct points at infinity, the conic, and this structure below gives the ordinarity above, if you just play a little bit. And so the maximal subgroup of PGL2Q that we lift, in this case, is the dihedral group of order 2 times Q minus 1 acting on these two rational points, okay? Which is another one of the geometric large maximal subgroups of PGL2Q. And in fact, the the lifted group with the Galois group is the whole group of automorphisms, at least for Q odd, but it is likely to hold also for Q even, let's say. Notice that this curve has many automorphisms with respect to, it was a 34 maybe, but many automorphisms, the same power of G, the largest power of G that we can have for ordinary curves with solvable automorphism groups, okay? So this is a very interesting example. Well, if we just start from an ellipse, for simplicity, take P odd, so the reducible polynomial is just u square minus lambda v square equal 1 with lambda a non-square in Fq. So the 2 points at infinity are not Fq rational. Then what we get is still an ordinary curve, but the value of P rank and genus is q square minus 1. We inherit the dihedral over the single group of order q plus 1, the last large maximal subgroups that we have in PGL2Q. And this is very often the whole automorphism group. And also the size is this one. So we can say that we have new, maybe interesting, ordinary curves with solvable automorphism group attaining up to the constant, the upper bound by Korczmarek and Montanucci Speziali. Up to a suitable change of variables, the model is even easier, somehow similar to the art in Mumford. It is that one. Okay, if 2 minutes. We can now extend these such games and say, okay, not anymore conics, but rational curves, C, and we want to lift not a maximal subgroup, but the whole PGL2Q. Is it possible? And preserve, also to preserve ordinarity. Remember the bound by Nakajima and also the bound for P odd G to the 7 over 4 that we heard before. Well, if you think a little bit about it, what we need is that the curve has Q plus 1 points at infinity, and the whole automorphism group PGL2Q acts on these Q plus 1 points. Okay, we were able to find such a curve, which indeed has another model which was mentioned by Ziv some years ago, but it is the same curve. And this curve has many automorphisms. Many in the sense that it is G to the 5 over 3. The largest known ones, actually, for infinite families of ordinary curves. I'm gonna finish because playing further on it, we extended this Ziv curve to the odd case. Forget all the details. This is indeed an extension, a generalization to the odd case of this curve, and we are also able to determine the full automorphism group, which I didn't talk about, but often it is not that easy to say there are no other automorphisms. This was part of the job. Okay, and that's all, and thank you for the attention.
Thank you for the nice talk, Giovanni. So, questions, comments?
Just one question. Sorry, thank you for the beautiful talk. So just a small question. So you say that it's not possible to compute, to do this work if you have a generic conic, but what if you just perform some fine change on U and V?
Yes, defined over which field? Because everything...
Which one you want, I mean.
Of course, I hid to say a lot of things. The point is that I'm always keeping fixed the shape of the Artin-Schreier extension. You know?
Yeah, exactly. Why don't you change this? Like, instead of U, like U plus something, or U plus V plus something, and I don't know. So instead of
Sorry, once again.
So
You want to
instead of-
perform in a transformation on the UMV?
on the UNV below in a way that it becomes something nicer,
Yeah.
but clearly you have also to change above. So the Artin-Schreier extension is, I don't know, x to the power q minus x equal to u plus v plus something.
No, but then the point is somehow difficult, not difficult, but the point is to define automorphisms above, okay? So you start from below, and with respect to the shape of the conic and the automorphisms of such conics, you are or are not able to define such automorphism on the y and z, inducing those automorphisms of the conic. So yeah, I don't know the shape of the resulting linearized polynomial on the left. Of course, up to suitable changing them, they will correspond to different conics below. Is this what we're talking about?
Oh,
Maybe not.
Later. No
Later,
problem.
okay.
Thanks.
Thank you. Any other comments or questions?
Do you believe that any of the examples you show of curves that you obtain by lifting some specific maximal subgroups could be unique with respect to that property, say fixing the genus and the group that you are lifting?
We are thinking on it, also, as you can imagine, inspired by analogous properties for the known ones, and with the known ones, of course, where is it? I mean this, as you know. And yeah, one may try, and we are trying, hopefully, to characterize somehow. One technique may be, as for Artin-Schreier, to characterize from below, with the suitable subfields. And so the first aim is to characterize this one, say the single curve, and possibly also for the Ziv even and Ziv odd curves, from below, trying to characterize them, just in terms of structure of the automorphisms and genus. Maybe it could be enough.
Okay, thank you.
Thank you.
Thank you, Giovanni. We don't have any time for more questions, so if anyone wants to talk, Giovanni, to be welcome.